Okay, welcome to Dynamics. I'm Dr. Everett. This is MECH 2340. And when some of the things that you need to be aware of is there's a Blackboard page, which I have open over here. And there is a syllabus, which you can download. The syllabus has the book title, the ISBN numbers, and all of that for the course. And in particular, we're going to be using the Mastering of Engineering, which is a computerized homework material, so it has the syllabus has the ISBN numbers for that. The statics class also uses Mastering Engineering. So if you go to the bookstore, make sure you buy the correct access code, because if you buy the statics access code, you won't be able to get into the class. The mastering account will need a course ID, and the course ID is Everett Dynamics, I believe. And so when you try to register, if you have difficulty, send me an email. Let me know what the situation is, and I will get it resolved. There will be a class response system. It's built into the mastering program. The only thing that you need is a Wi-Fi enabled device. That could be a laptop or your smartphone. I will use the in-class response to be checking attendance, and so if I don't get a response from you, I will assume that you're absent, and if you're absent for too many days, I have the option of dropping you from the class. So don't miss too much. The course description is included in here, and the method of grading is also included. The course outcomes are listed so that you know what it is that you'll be learning. The exams, I do not give makeup exams. If you have an excused absence for an exam, I will count the next exam grade twice to make up for it. Participation, you will get credit for participating. We'll try to do problems in class, and we'll use the response system for you to respond, and that's how you'll pick up your participation credit. One of my favorite quotes came from Albert Einstein, who said that insanity is doing the same thing over and over again, expecting different results. So the point about this is that if you are doing something that causes you to fail the first exam, then you should be looking at trying to do something different, because if you continue to do what you're doing, you'll probably fail the second exam as well. So pay attention to what's happening and be successful. Okay, in addition to the syllabus, the Blackboard talks about a program called Mathematica. Mathematica is a nice program that does mathematics for you, and it's free to UTEP students. You can download it on your personal computer at home. If you want to bring it to exams, you're welcome to use it during exams as well. This document shows you how to get Mathematica and how to install it. And there's also some learning material. So there's a couple of links in there that talk about how to use Mathematica. And I'll try to teach that as well in the class. So be sure to check out Blackboard. The Mastering Engineering, the class response system is going to be used very quickly. So I recommend that you get on that and get the Mastering Engineering on your computer as quickly as possible. Okay, one of the things that's going to happen is you will be solving problems, and the purpose of this class is basically twofold. One is to be able to solve textbook type problems, which will get you a grade in this class. But the second purpose of the course is to teach you how professionals approach dynamics problems, give you the practical aspect of that. And so I will give you my experiences and the things that I have learned working as a professional in this area of dynamics. And so I will give you rules of thumb and ways of approaching problems that are probably different than anything that is found in textbooks. And one of the things that I like to do is to ensure that students are able to approach a new problem and be able to tell what to do. So one of the things that I'm going to teach you to do is to count degree of freedom. And basically, degree of freedom is the number of things that can move independently in a problem. It makes no sense right now, I understand, but as the time goes by, I hope that you'll, through examples, will be able to learn what I mean by that. And then you also identify what it is that you're trying to find or solve in the problem. And these two things together will tell you a little bit about whether you need to draw free body diagrams or if you need to calculate forces or things of that sort. So this will be a recurring theme, and we'll just use these questions over and over again so that you can be able to approach problems in a systematic way. The last question that I'll be asking, and these will be added to as the course develops, is whether or not time is passing by in the problem, and if so, then you approach problems in a different way than you would normally do. Okay, so to get started on this, let me show you the basic equations that we're going to be using in Chapter 12. We will have a number of definitions, one of which is position. The position of an object is given by distances measured along directions. So when we first get started, we're going to have one direction, so things are going to be moving along one axis. And the position of something is going to be given by a coordinate. I'm going to call it x. And so if you tell me that the direction is east, for example, and that you have a position of 3 to the east, okay, one of the things that we'll be talking about in this class is position. In order to know the position of something, you have to have an origin, a direction, and a distance. So, for example, if you have an automobile, let's see. So here's an automobile, and you want to know where that automobile is. You'll choose an origin, which will have to be known by everybody. So, for example, maybe it's downtown El Paso, and you'll have to have a direction. So maybe this is the Mesa Avenue, or Mesa Drive, whatever. And so that's a road, and then you would have to give me a distance, which I'll call just a variable x. So if you tell me that you are measuring position along Mesa, the 0 position is, say, Mesa and Franklin, or whatever intersects that, and that you are 2 miles north, then I would be able to figure out where you're located, and that's your position. If you want to know how fast somebody's going, that is referenced by the velocity. It's usually written as a v, and by definition, velocity is equal to the time rate of change of position. So that's the way it's defined. People talk about speed, and I believe your book uses S for speed. Speed is equal to the magnitude of velocity. Velocity is a magnitude, the speed that you're traveling, and it's also the direction. So for example, in this example, if the direction is along Mesa and you're headed north, then you could say, well, I'm doing 30 miles an hour north, and that would be your velocity. If you told people that you're doing 30 miles an hour, then you're just telling them the speed. In addition to the velocity, we have what's called acceleration. The acceleration is the time rate of change of velocity. It also has direction. So when you talk about acceleration, you would give me a magnitude, how big it is, and you would also tell me what direction that you're traveling. Occasionally it's convenient to use another formula for acceleration, which goes when velocity is given in terms of position, v dv dx, and that's given in the textbook. You can see where that comes from, and that is equivalent to the derivative of velocity with respect to time. Occasionally we'll have problems where you start out knowing the acceleration and you're interested in finding the velocity or the position, and to do that, then you would do an integral, and you've done derivatives and integrals in math class, so I assume that you can do the basic differentiation and integration that we might run into here. So for example, if you know the acceleration, then you would find the velocity by taking a integral. So dv dt, for example, is equal to acceleration. Then you just multiply through by the dt, and then you would integrate both sides. Do these two integrals. On the left hand side you'd have velocity, and on the right you would have the integral. Depends on what the a is, but like I said, I assume you can do an integral plus an arbitrary constant, which is your initial value. If you wanted position, then velocity is equal to dx dt, which is equal to the integral that you've got here. So you'll do that integral first, and so whatever you come up with is here. Then you'll multiply through by dt and integrate both sides, and that gives you the position then is equal to the integral of the velocity dt plus another arbitrary constant that gives you the initial position. And if you have the acceleration given in terms of position rather than time, you could start with this one and you would do something of this nature. v dv is equal to your acceleration, which would have x squared or whatever instead of time, times dx, and now you can integrate again, and you'd integrate the left hand side. You'll get 1/2 v squared, and this would be the integral of your a plus an arbitrary constant for the allowing initial conditions. So essentially that's the relationships between positions, velocities, and accelerations. All of chapter 12, virtually all of chapter 12 uses these derivatives and integrals to relate the values together depending on what it is that you're looking for. Okay, so if there's cases where that occur frequently, especially in textbook problems, where the acceleration is a constant, and in that case you can do the integrals, but there's very little reason to do them over and over again. in your book derives equations for constant acceleration. And here are the equations. You can certainly look in the text and get the derivations of those. But if you have constant acceleration, then the formulas that follow by integrating would be the velocity equals initial velocity plus the constant acceleration times t. Now, your book doesn't use this, but has initial time. Your book sets up all problems so that initial time is 0, in which case t o is 0. I like to put it in there. It's certainly this equation is true, and it helps solve some of the problems that you'll run into in the text. If you integrate again, you'll end up with an equation for the position, and it'll look like this. Position equals initial position plus initial velocity times time minus time initial plus 1/2 acceleration, constant acceleration, this is all constant acceleration, time minus initial time squared. There's a third equation that comes out when you use the acceleration equals v dv dx, and it looks like this. Velocity squared is equal to initial velocity squared plus 2 times the constant acceleration x minus initial x. And so we're going to use these equations quite a bit in Chapter 12. So you might want to commit them to memory or carry them around in a someplace in your notebook that you can get to them quickly. Okay, so essentially that's the theory that I have for this particular chapter. The next thing I'd like to do is just start working problems and showing you how to use these equations and the definitions of velocity, acceleration, etc., to actually solve problems. So I think the next thing is to actually do some problems then.